Hi, I want to give you a brief overview on liquids. So liquids, these are going to be molecules that are close together but not in a fixed position. They can move, and the word that we use when those molecules can move around one another is translate, that the species can translate. They can move around one another. Now, I want to do just a really quick review of mixtures and then jump into some in-depth items. So you'll recall a heterogeneous mixture means that we have two or more substances that come together, but they maintain their own composition. Now at the macroscopic level, their properties don't change. So here's a basic example. I'm going to mix lettuce and tomatoes. Their compositions don't change. I look at them, yeah, they're still just lettuce and tomatoes, the same properties. If I have, let's say, iron and sand, I can see they have their own composition of iron and sand, even though they're mixed together. Now these can be separated with filtration. Let's say that I have some sand and water. We could just filter out the one substance, the water, and have the sand remain. Now the homogeneous mixture, you'll recall that we bring substances together and they create a new composition, like a cake batter would be a really good example. We don't necessarily have a chemical reaction when I have cake batter. I haven't baked it. There's no chemical reaction. But when I bring the eggs and the flour and the sugar and the milk together, it is going to create this new composition, and that is a homogeneous mixture. Now remember, our special word for a homogeneous mixture is solution, a solution. So I want to talk about these homogeneous mixtures. The solute, it can be a gas, liquid, or a solid dissolved in that liquid. So I have my one liquid, and I can put any of those three phases in, and it can dissolve. Let's see, we could have CO2, carbon dioxide, dissolve in water, and that's a gas. I could have a solid, I could have table salt that's going to dissolve inside of the water. A liquid, I could squeeze an orange and I could put that juice from the orange in the water, and that would dissolve. Now, we mostly do a lot of dissolving of salts, of ionic compounds in water when we're in a first year chemistry class. And I wanted to remind you that when you do this ionic dissolving, you test it with a conductivity probe. You'll recall that ionic compounds, when they dissolve in water, they conduct electricity. So if you want to confirm that you have an ionic compound dissolved in water, there are ions in that water, here you live. You're going to do a conductivity test. If it conducts electricity, you have ions in that water. Now, if we look at a solution, it has the same composition, this consistent one composition. So at the macroscopic level, everything, the properties look the same. At the microscopic level, though, the properties are different for these components in the mixture. Now, a little bit on separation. Separation is going to be based on intermolecular forces. So that means we can't do filtration. It's not just a, hey, let's get a piece of filter paper and pour water through. We'll catch all the ions. That's not how it works. Those ions are surrounded by the water. They're going to go through the filter paper. So we can't use filtration. I put it right here. You cannot separate with filtered paper. We're going to have to look at the intermolecular forces. One of the great ways that we do separation is with chromatography. When I worked as an organic chemist, this is what I did for years. I was a gas chromatograph mass spectrometer, gas chromatograph. I would separate really, really nasty, great big carcinogenic semi-volatile compounds. I would separate them, evaporate them into a gas, and then separate them with this column. And it was really cool. The column, based on its polarity, it would interact with these gas molecules. If the gas molecules had dissimilar intermolecular forces, they would just fly through that column and come out like 30 seconds later. If the gases I put in there, the molecules, had very similar intermolecular forces, they would attract and bump and stick and mosey through, because they were attracting like they were friends, through that column, and it might take 26 minutes for that gas molecule to come out. And that's how I separated. I could have 160 different molecules in one sample, put it all in, vaporize it, send it through this column, and they'd all come out one at a time based on intermolecular forces. It was the attraction between the molecule, its intermolecular forces, and the intermolecular forces of that column. It's like this sticky goo inside the column. Now, on chromatography, you can do paper chromatography. That's what we do in a high school or a college lab. You have filter paper, you'll put maybe a dot of ink on it, then you put in water or isopropyl alcohol, and as that water absorbs and moves up, or the isopropyl alcohol absorbs and moves up through that paper, the intermolecular forces of the species inside that dye, the molecules in the dye, it will either attract to the solvent, whatever is moving through that paper, or it won't attract. If it attracts, it moves with the solvent, and if it doesn't attract, it stays at the bottom, and that water, for example, just keeps on moving through the paper. So we use paper a lot. In industry, we use columns, and that was the column I was talking about. But same principle. You have a stationary phase, and then you have this mobile phase, and the mobile phase is what we're trying to separate. The stationary phase is what we have, either paper or a column. When I say column, it's just this really long tube with this goo inside of it. Now we also have gas chromatography and we have liquid chromatography. Almost everything that we do in a college lab or a high school lab is going to be liquid chromatography. Gas chromatography, you actually need a GC, gas chromatograph, and those are that's going to be really expensive. I will tell you this though, we do have high performance liquid chromatography, HPLC. If you are good at HPLC, you can make bank. It is a really good field. You can work all over in the medical industry, in medical lab work. If you're good at HPLC, that would be a good career. Or if you enjoy lab work, this could be a good career, is get to know HPLC, high performance liquid chromatography. Okay, another way that we can separate our homogeneous solutions is distillation. And this is, again, back to intermolecular forces. It's going to be separation based on boiling point and vapor pressure, which is intermolecular forces. And then wanted to point out that, again, these homogeneous solutions, they do not scatter light. Heterogeneous solutions will, but homogeneous solutions don't scatter light. And that means that they don't have that Tyndall effect. You'll only scatter light, have the Tyndall effect, if it's a heterogeneous solution, like fog. That would be little water molecules suspended in the air. That would be a heterogeneous solution. It scatters light. So there is a brief overview for you on liquids. Have a really good day. If you have, there's so many videos that I have on solids and liquids, intermolecular forces. If you have any questions, go to LeanThink for YouTube or leanthink.org, the website. Thanks, have a good one, bye.